All right, today we're going to find the lengths of polar curves, and we're going to use the parametrics. X is equal to r cosine of theta, and then y is equal to r sine of theta. So we're going to use these parametrics to be able to find the lengths of the polar curves using the length formula that we know from a previous video for finding the length of really rectangular curves or functions. So what we know is that the length of a curve, L, is going to be equal to the integral from, let's say a to b, of the square root of dx dt squared plus dy dt squared dt. So what we want to do is we want to transfer this formula into polar form. So in order to do that, I'm going to need to know dx dt and dy dt, but we're not really going to use t's this time because now our function's in form. Well, actually, let's put these in t's, and then we'll have that right. So if I wrote those as t's as opposed to thetas, and now remember t represents the angle, I need to find their derivative. So finding the derivative, dx dt, well, in order to do this, this is a product, so we're going to have the product rule. So the derivative of the first times the second plus the first times the derivative of the second, but the derivative of the cosine is negative sign. And then similarly here, if I want to find dy dt, it's going to be the derivative of the first times the second plus the first times the derivative of the second. All right, so now I can plug these into here, and you'll be surprised, even though it looks pretty scary, they simplify nicely. So if I'm going from alpha to beta, now we're going to go from our t values. So this is going to be the integral. I'll talk about it in a second. So this is going to be the square root of r prime cosine of t minus r sine t squared plus r prime sine t plus r cosine of t squared dt. And we're going to go from alpha to beta. So now everything is a function of t, so we're using these limits of integration. Now, simplifying really means we're going to have to square these things. So this is going to be equal to the integral from alpha to beta of the square root of. Now we're going to have to square this, and then it's going to be outside multiplied by inside. So this is going to be r prime squared cosine squared of t plus, well actually not plus because they're both negative. So outside and inside is going to be r prime r sine t cosine t, r prime r sine t cosine t, and then last is going to be this thing squared, so plus r squared sine of t. And for this one, we're going to have something similar. This is going to be this squared, so r prime squared sine squared of t. Now outside and inside is going to be exactly the same thing as this, except a plus. So r prime r sine of t cosine of t, and then last we're going to have plus r squared cosine squared of t dt. So one thing we immediately noticed was that cancels. And then another thing that I noticed is that these things share the same coefficient of r prime squared, and then similarly these share the same coefficient of r squared. So I can factor those things out. So this is the integral from alpha to beta of, let's do the square root. So if I factor out the r prime squared, I'm going to have cosine squared plus sine squared, or I'm going to write it as sine squared plus cosine squared because most people recognize the Pythagorean theorem in that order a little better than the other one. And the next one, I'm going to factor the r squared out, so plus r squared, and then I'm going to have sine, I missed my square, didn't I? Nice work. Sine squared of t plus cosine squared of t, and this is going to be dt. All right, now we know that each one of these things is equal to 1. So that's 1, and that is 1. So what we're going to get, I'm going to write this in this form. alpha to beta of the square root of, let's do the r squared first, it tends to come first in books, plus, now this is r prime squared, so let's go r prime, which is going to be dr dt squared, and this is going to be with respect to t. Now, many books don't use t, they use theta, so let's do this from theta instead, but it's just going to be a dummy variable change, so r squared plus dr d theta squared d theta. So just let t equal theta, so then dt equals d theta. All right, so that's that formula we're going to use. I'm going to pause this, come up with an equation, and then we will put this into practice. A trivial equation, just so I can make sure that this formula makes sense to us. So determine the length of this curve r is equal to 5 from alpha is equal to 0 to beta is equal to 2 pi. So we know r equals 5 is a circle of radius 5, and we're going to go from the radial 0 all the way to the radial 2 pi. So, or the angle 2 pi. So we're really finding the entire length of this circle. Now, when we find the length of the circle, we're really trying to find the circumference of the circle. And what I know is from honestly, a middle school class, that circumference is going to be 2 pi times r. So this should be equal to 2 pi times 5, which should be equal to 10 pi. So I want to do this using our formula, and then we'll find, of course, a much more complicated a polar curve, and then find that thing's length. So using this, I know the length is going to go from the integral from 0 to 2 pi of the square root of, well, r is 5, so this is going to be 5 squared, plus, well, this thing's derivative, so dr d theta is going to be equal to 0 squared d theta. So this is the square root of 25, which is going to be 5. So this is the integral from 0 to 2 pi of just 5 d theta, which is equal to 5 theta evaluated from 0 to 2 pi. So 5 times 2 pi and 5 times 0 is equal to 10 pi, as we expected. All right, so let me put a slightly more complicated curve up here, and we'll find the length of that. So a new example is going to be find the length of the cardioid. And I know I keep coming up with formulas that look very similar to this, but you see that a lot. You see a lot of the cardioids of 1 minus cosine of theta, which looks like this. 1 plus the cosine of theta, which really looks like this thing flipped. 1 plus the sine of theta, which will be, just shifted basically 90 degrees or 270 degrees, and then 1 minus the sine of theta. So really, if you look at this curve, we tend to shift it in all 4 directions by an angle of pi over 2, and then find these things. So the length of this will also be the same length as 1 plus the sine of theta, or 1 minus the sine of theta, and so on. So this is a good enough example to do. So if I want to find the length of this curve, I really want to go from, from 0 to 2 pi. So the entire length is going to be from, this angle 0 and then all the way around to 2 pi. So we're going to find the entire length. So L is going to be equal to the integral from 0 to 2 pi of, I should find r prime, or dr d theta. So the derivative of 1 is going to be equal to 0. The derivative of cosine is going to be negative sine, so this is going to be equal to the sine of theta. So this is going to be the square root of r squared plus dr d theta squared d theta. So this is going to be the integral from 0 to 2 pi of the square root of, this thing squared, 1 minus the cosine, that's not right, the cosine of theta squared, plus this thing squared, which is going to be the sine squared of theta, d theta. So we'll do some simplification and see if there's any thing we have to do here. So L is going to be equal to the integral from 0 to 2 pi of the square root. So squaring this, we're going to have 1 minus 2 cosine theta. 1 times 1 outside is minus cosine, inside is minus cosine. So that's going to give us minus 2 cosine, and then cosine times cosine, and the negative is going to give us positive cosine squared of theta. And then finally plus sine squared of theta. So I spotted the Pythagorean theorem right here, which is going to give us 1. So really what we're going to get is we're going to get 2 minus 2 cosine of theta. So, that's equal to 1. So this is going to be equal to the integral from 0 to 2 pi of 1 plus 1 is 2, so this is going to be the square root of 2 minus 2 cosine of theta d theta. Now, a lot of times in our links, even in like in the beginning of Calc 2, when we were trying to find the length of rectangular curves, or of y is equal to f of x, or x is equal to f of y, or their parametrics, we had the square root of an expression, and half the time you would notice that the radicand was a perfect square, or in order to integrate it ended up being some type of u substitution. So in this case, it ends up being kind of related to a perfect square that we have to recognize a common thing that says, well, actually, let's kind of derive this to show you. We've used this formula. I'm going to do it in a different color just for the work. So if I have the cosine squared of theta, we use the fact that that is 1 plus the cosine of 2 theta all over 2. And then similarly, if we have the sine squared of theta, this is equal to 1 minus the cosine of 2 theta all over 2. So what I notice is I have a subtraction of theta. So I don't want a 2 theta in here, and I also don't want the 2. If I rewrite this is going to be 2 sine squared of theta is going to be equal to 1 minus the cosine of 2 theta. So we're getting close. We're getting close. If I double this, we're going to get 4. So over here, I'm squishing it in. So 4 sine squared of theta is going to be equal to 2 minus 2 cosine of 2 theta. So I'm so close. This says theta, this says 2 theta. So what I'm going to do is I'm going to do a substitution. I'm going to let let's call this t because it's any dummy variable. So we'll just call this t so that I can use the thetas I have down here. If I let t be equal to theta over 2, so if you let t equal theta over 2, then what's going to happen is this thing will become theta, and this thing will become theta over 2. So really what we have here is we have, so slide it over here. So this would be 4 sine squared of theta over 2 is going to be equal to that expression, 2 minus 2 cosine of theta. So substituting this 2 minus 2 cosine of theta for this expression right here, this is now going to be, L is going to be equal to the integral from 0 to 2 pi of the square root of 4 sine squared of theta over 2. So we tend to be using this identity a lot when we're integrating our polar curves. So now what we know is that we have to be careful with square roots. So things that we talk about in classes, is this true? That's really kind of like a big question we ask. And the answer is no. Well, technically, sometimes it depends on x. If x is positive, it's true, but if x is negative, it's not. So really, what we have here is the square root of x squared is technically the absolute value of x, and the absolute value of x is redundant if we are talking about positive values, and that's the case that we have here. That this radicand is actually positive from 0 to 2 pi, because we're talking about a sine squared. So your sine function does bounce between positive and negative, but when you square it, it actually makes everything positive. So this is a positive expression. So if for completeness, what I would do is this would be the integral from 0 to 2 pi of the absolute value of the square root of this square root of this. So this is 2 sine of theta over 2 dt. But since it's positive, we're good to go. Okay, so and so we can actually kind of verify that too. That this curve here, when we're talking about theta over 2, that we're really talking about something like here, but we're going from 0 to 2 pi, so we're technically going from here to here. So we're talking about just this part of this. Okay, so it is positive, so we're good to go. So now I can take its antiderivative, which is going to be negative the cosine of, let's get rid of this, I don't need you anymore. So this is going to be equal to minus say 2 times the antiderivative of this is going to be minus the, I don't know why I got a minus there, I had a minus here. So this is going to be cosine, so that's where that negative comes from, the antiderivative of this. This would be theta over 2 divided by its coefficient, which is going to be 1/2. So this is going to give us a negative 4. So this will be equal to negative 4 times the cosine of theta over 2 evaluated from 0 to 2 pi. So evaluating the top, minus 4 cosine of 2 pi over 2, and then minus a minus 4 cosine of 0 over 2. So the cosine of pi, which is going to be here, which is going to be, this is going to be negative 1. So this is negative 1 times negative 4, which is going to give us 4. And then the cosine of 0, the cosine of 0 is going to be here, which is going to be 1. So negative 1, 0. This is going to be 1 comma 0. So this would be 1, so this would be plus 4. So what I get is I get a length of 8. So this thing has length 8, which I find extremely interesting, that we're talking about a radial curve that is 1 minus the cosine. So we're talking about this trig function, but it has integer length, which is pretty cool. That has, a whole number length. And that's it. I'll see you soon.